Today we'll be looking at how energy and power flows through resistor circuits, circuits that have only resistors in them, at least for the moment. Batteries supply EMF to a circuit, but they also provide energy. The chemical potential energy of the reactions in the battery transforms into kinetic energy the charge carriers as they move, and eventually into heat as the charge carriers collide with the nuclei in the resistor. So as we go through here, but what's really happening is they're bumping along, and so they're giving up some. Now, in our zero resistance wire model, it only happens here in the filament and so on, but all the power that comes out here has to be radiated. Consider some infinitesimal charge dq as it traverses the circuit. In passing through a battery of EMF E, the charge gains some potential energy du according to simply du equals dq times E. Remember, this is coming back from our ultimate thing, which was that delta U is Q delta V, because V is defined as the potential energy per unit charge. The energy divided by the battery over its entire lifetime would be total U, and it would be total charge Q times EMF, but that turns out not to be particularly useful. Much more useful is the rate at which the energy is added to the circuit, that is, the power delivered by the battery. If it takes the time dt for the charge to cross the battery, then the power would be P battery, which is du dt, which is dq times E over dt, which is dq dt times E. And we're playing a little fast and loose with the calculus there, but not too bad because batteries have constant EMF, so we can just treat it as coming out front. But remember that dq dt is the current. And so P battery is just the current times the EMF, I times E. And that's worth knowing. This is true for any circuit element that delivers EMF, that it must deliver power, which is the current times the EMF. The more current you draw, the faster you draw down the battery, which certainly makes some sense. Note the units are going to be volts times amps, but a volt is a joule per coulomb, an amp is coulomb per second, so we get joules per second, which is, of course, a watt. So, as expected, power is measured in watts. All right, consider a simple circuit here. What we get is that the battery raises the potential energy of the charge, which then flows through the wires, hits the resistor, bounces around in some crazy random manner, which is turning this potential energy into kinetic energy into, as it bounces around, randomness and thermal energy, and then the charge carrier comes back. So now we see that the charge dq loses energy as the resistor gets heated. We say the resistor dissipates the energy. It takes it out of the system. We can see the potential energy change here is delta U is dq times delta VR. We need to be careful here because we're saying voltage drops across a resistor, so delta VR is negative, so delta U is also negative. The charge is losing energy as it goes through the resistor. With the same sort of reasoning, we can find the power transferred out of the current into the resistor is P sub R, which is I times delta VR. And that's one you're going to use a lot. Since delta VR is minus the EMF, at least in the simple circuit, we see that the power of the resistor, power lost into the resistor, is minus the power gained at the battery. All right. So the total power, the power added by a battery and then lost to the resistor, is zero identically. It's always the same, which is what we expect from conservation of energy. What current in amps is drawn by a 60-watt reading lamp when plugged into a standard outlet of 120 volts? We should keep something in mind. Standard outlets aren't DC. There's not a battery plugged in somewhere that's delivering 120 volts constantly. It's really AC, and we'll talk more later in the class about what that means. So right now, let's pretend that it delivers a fixed 120 volts instead of the sort of fluctuating thing that we have here. Then it becomes relatively easy since the power equals the current times the voltage drop. We can say that 60 watts is the current times 120 volts. So the current in this reading lamp would be about half an amp. Remember, that's reasonable. That's about what appliances in the home will do. Somewhere between a tenth and 1 amp is pretty typical. Since the resistor obeys Ohm's law, we know that delta VR is I times R. This lets us find some alternate forms for the power. I should be careful here. I'm probably not being 100% consistent. Here we're saying that this is the size of the drop. So it drops by 7 volts or whatever. So this number is actually being treated as a positive, even though really delta VR across the resistor should be negative as the thing drops. But it's kind of traditional in engineering circles to treat the voltage drop as a magnitude and then put the minus sign in explicitly. So I think we'll do that from here on out. All right, so we say power equals I times delta V. But remember that I is delta V over R. So I can kind of replace this with this and then multiply these out, and I get delta V squared over R. Or I can replace delta VR with I times R and square it, divide by R, and we get the power is also I squared R. So power is IV or V squared over R or I squared R. That last one gets immortalized in engineering schools as a little nursery rhyme of twinkle, twinkle, little star, power equals I squared R. All right, consider 2 wires connected to a battery, each with its own resistance. When the circuit is complete, and I should say connected in series to a battery, each with its own resistance. When the circuit is completed, which develops more power, the high resistance wire or the low resistance wire? And here we see the experiment.
In this demonstration, I have 2 lengths of wire, a length of nichrome wire, which has a resistance of 2.7 ohms, and a length of copper wire, which has a resistance of 0.1 ohm. Both of these are connected in series and will be connected to this large battery here. Now, the question is, when I complete the circuit, when I connect this lead to the battery, what will happen to these pieces of paper resting on the wire? Will this paper burn because the wire heats up so much? Will this piece of paper burn because the wire heats up so much? Will they both burn because I'm sending a tremendous amount of current from this car battery into these little wires? Or will neither of them burn because metal is a good conductor of electricity? So as you can see, quite quickly, the paper on the nichrome wire starts to burn and has now come off. This is because the nichrome wire has a higher resistance than that of the copper wire. Both pieces of wire were receiving the same amount of current because they're in series, but because the resistance is higher in the nichrome, and the I squared R law tells us how much power can be delivered to each piece of wire, more heat was generated in this wire, causing the paper to burn.
By the way, there was a little bit of a hint if you looked really closely. There's scorch marks here from previous versions of this experiment. You can see that it's been blackened because of the heat that's been developed. So there was sort of a cheat if you looked ahead. All right, a 60-watt bulb is rated for operation 120 volts. That's the standard one. What power in watts does it develop if you use a dimmer switch to reduce the voltage to 90 volts? Well, the power that comes out at 90 volts will be V squared over R. And the power that comes out at 120 volts would be the 120 volts squared over R. So we might want to just take their ratio, and we find that P1 over P naught, well, the 1 over R's would cancel, and we get V1 squared over V naught squared, which is V1 over V naught quantity squared, which is 90 volts over 120 volts squared, which is 3/4 squared, which is 9/16. And therefore, the actual power would be 9/16 of the original power, which turns out to be something like about 33 3/4 watts. No, it's just about half. By reducing the voltage by 1/4, we reduce the power by almost half. Draw a blue circle around the resistor or resistors that dissipate the greatest power, and a red circle around those that dissipate the least power. In each case, of course, the power will be the actual voltage squared over the resistance. So we'll take A as our standard, and that would be delta V quantity squared over R. But for B, for instance, it would be 2 delta V quantity squared over R, which is 4 times the original. And likewise, over here for C, we would have delta V quantity squared over 2R, which is half as much. And then over for the fourth one, we'd have delta V over a half R, which is 2. So we can see that this is the greatest, and we can see that this is the least.